Impedance. Introduction. The impedance of a busbar system comprises three components: resistance, inductive reactance, capacitive reactance. In a DC circuit, the steady-state current will be proportional to the applied voltage and depends only upon the resistance. Inductance and capacitance also play a part in transient conditions when switching on and off a circuit. In an AC circuit, the steady-state current will be proportional to the applied voltage and depends upon resistance, inductive reactance, and capacitive reactance. Inductive reactance is proportional to the frequency, while the capacitive reactance is inversely proportional to the frequency. Resistance is frequency dependent. These three parameters are most crucial in the design of the busbar systems, as they quantify and help in keeping the constraints imposed by the specification on temperature rise, power loss, and voltage drop, or a selected combination of the three. Resistance. Resistance is a measure of the opposition of the flow of current in a conductor when a DC voltage is applied across its ends. If an AC voltage is applied across the ends of a conductor, opposition to the flow of current is offered not only by the resistance but also by inductive and capacitive reactance. Resistivity is a specific property of the conductor material, and it increases with the increases in temperature. Beta is the coefficient of resistivity and alpha is the coefficient of resistance. There is a marginal difference between alpha and beta, even though DC resistance R and resistivity ρ are related by a linear equation. The reason is that with the increase in temperature, the length and area of cross-section of the conductor will increase depending upon the coefficient of linear expansion of the material of conductor. Table 5.1 details coefficient of resistivity and linear expansion of copper and aluminium. Since the order of coefficient for linear expansion for copper and aluminium is 2 stages behind the order of coefficient of resistivity, the difference in the value of alpha is marginal and can be taken to be equal for both the material. When a conductor carries alternating current, its resistance value RAC is always more than RDC at the same temperature. As will be seen in the following discussions, the increase in the resistance is due to skin effect, when in isolation, and a combination of skin effect and proximity effect, when with an adjacent conductor, of the same phase or different phase, carrying current. Skin effect. The skin effect is the phenomenon that concentrates the flow of an alternating current nearer to the outer surface of the conductor. This phenomenon is much easier to explain with a round conductor, though it can be extrapolated to any profile. The current density will be maximum at the outermost surface, or at the skin, and reduces as the distance increases from the surface to the center. The variation in the current density will depend upon the resistance or resistivity and the frequency, the rate of variation. The effect will be more pronounced with increasing frequency and lesser resistance. Comparing the two most commonly used materials for the conductor, the skin effect, at a given frequency, will be more pronounced in a copper conductor than in an aluminium conductor, as the conductivity of copper is higher than that of aluminium. Overall, skin effect increases the resistance of a conductor. Skin depth is also a function of the permeability of the material. Table 5.2 displays the skin depth of copper, aluminium, and steel at a frequency of 50, 60, and 400 cycles per second. Interestingly, even though the conductivity of steel is not much lower than that of either copper or aluminium, its magnetic permeability is extremely high. Consequently, the skin depth is extremely small. Therefore, iron, as an electrical conductor in the AC circuit, is very poor. Proximity effect. The phenomenon of proximity effect is similar to that of skin effect, except that the current density is altered by the magnetic field created by the adjacent conductor as well. This is more pronounced with the increase in frequency and decrease in distance between the conductors. Unlike the skin effect ratio, the proximity effect factor not only depends upon the physical shape of the conductor, configuration, and proximity to the neighboring conductor, it will also depend upon the direction of the current in the neighboring conductor. Direct proximity effect. This is the distortion to the current density due to the presence of neighboring conductor of the same phase carrying current in the same direction. In a busbar system, each phase can comprise many conductors running in parallel, carrying current flowing in the same direction. Such configuration of a phase conductor is very common in low and medium voltage bus ducts and high current open bus connections in arc and induction furnaces. Inverse proximity effect. This is the distortion to the current density due to the presence of a neighboring conductor of a different phase carrying current flowing in the opposite direction. Any low and medium voltage connection will have a return conductor, in single-phase connection, or another phase, in three-phase connection, running nearby. In a three-phase circuit, the current in the adjacent phase will run in the same direction, parallel, or the opposite direction, anti-parallel, in a periodic manner resulting in a direct or an inverse proximity effect. Induced proximity effect. Any metallic object in the neighborhood of a conductor carrying alternating current will have induced eddy currents and consequently, losses. If the metallic object happens to be of magnetic material, it will induce hysteresis losses as well. Losses in enclosures of busbar systems and support structure fall in this category. These losses will be fed by the current carrying conductor, reflecting as increased resistance. Current density distribution in ideal round conductor. It is interesting to observe the current distribution in a round conductor subjected to the combination of skin effect and proximity effect. If the currents flow in the same direction, as in the case of two conductors in parallel of the same phase, then they tend to concentrate at the farther end of the conductors. If they are in the opposite direction, as in the case of go and return conductors in a single-phase system, then they tend to concentrate closer to each other. The asymmetry and distortion in the current density will be more with the decrease in distance. This current density distribution will pulsate in intensity at twice the system frequency in a synchronous manner. In a three-phase system, the neighboring conductors of a different phase can alternatingly carry current in the same direction and the opposite direction. Current density distribution in parallel go and return round conductors. Locus of the center of gravity of current densities for a three-phase system, with conductors arranged in line formation. Locus of the center of gravity of current densities for a three-phase system, with conductors arranged in delta formation. Combined skin and proximity effect. In a busbar system, there will be a neighboring conductor of a different phase and in some cases, parallel conductors of the same phase as well. The combined result of skin effect and proximity effect is felt when the busbars are close to each other. Figure 5.13 displays the current distribution in a bundled conductor comprising 10 busbars per phase. The formula for equivalent resistance when connected in series or parallel is as displayed. Inductance. The inductance in busbar systems is normally not of much concern for system engineers. The values are not significant when compared to overall values to alter any system parameters for calculations of fault currents and voltage drops. Evaluation of reactance is important in AC high current open bus as in the case of induction and arc furnaces, and long length of low voltage bus duct connection between the transformer and the incoming switchgear panel. Inductance is the property of an electric conductor by which a change in electric current through it induces a voltage. This property is called self-inductance. The current can also induce a voltage in the neighboring conductor which is termed as mutual inductance. A conductor carrying a current will produce a magnetic field. A current, varying with time, will produce a magnetic field that also varies with time and induces a voltage. This voltage will drive a current through a conductor to produce a magnetic field that will oppose the change. Hence the negative sign. The energy stored in an inductor is proportional to the inductance and square of the current through the inductor. The formula for equivalent inductance when connected in series or parallel is as displayed in figure 5.15. A conductor in isolation, when it is not affected by the flux generated by neighboring conductor, will have self-inductance. This is an ideal condition, and in practice, there will always be another conductor carrying current either in the same or in the opposite direction. The flux generated by the current in the neighboring conductor will alter the linkage. The linkage of flux with the neighboring conductor results in mutual inductance. If Ls is the self-inductance of a conductor and M is the mutual inductance, then the inductance of the conductor equals self-inductance less the mutual inductance. The inductive reactance is directly proportional to the frequency and the inductance. In a purely inductive circuit, with a sinusoidal AC waveform, the current will lag the applied voltage by 90 degrees. Capacitance. As mentioned earlier, the capacitance in a busbar system with air insulation in isolated phase bus, segregated and non-segregated phase bus, high voltage open bus, and high current open bus in furnaces is literally of no consequence. There is, however, capacitance of some significance in sandwich bus and low voltage cast resin bus, where the conductors are close to each other. Shielded conductors in solid insulation bus and medium voltage cable bus also have significant ground capacitance. Capacitance is defined as the charge required to raise the potential by 1 unit. A conductor possesses a self-capacitance in isolation and in the vicinity of another conductor will have a mutual capacitance. The energy stored in a capacitor is proportional to the capacitance and the square of the voltage across it. The formula for equivalent capacitance when connected in series or parallel is as displayed in Figure 5.21. The capacitive reactance is inversely proportional to the frequency and the capacitance. For a sinusoidal AC waveform, the current will lead the voltage by 90 degrees. In a purely capacitive circuit, with a sinusoidal AC waveform, the current will lead the applied voltage by 90 degrees. Voltage drop. Voltage drop is a very important design parameter in a power connection. Fortunately for a majority of busbar connections, the voltage drop is within the acceptable norms. There are, however, a few specific connections where voltage drop does become critical and needs to be looked into. AC high current open bus in arc and induction furnaces. DC high current open bus in metal extraction industries and chlor-alkali plants. Low voltage AC bus duct and cable bus of significant length. In a high current busbar system, the voltage drop is associated with significant power loss in the connections as well. In the arc furnace, the voltage drop will have a considerable impact on the performance of the furnace. In metal extraction plants, the voltage drop in the connections will significantly contribute to the overall cost. In low voltage distribution networks, a voltage drop will result in motors drawing more current and consequently more copper loss, resulting in their running below their optimum efficiency. Some regulations limit the maximum voltage drop in a low voltage network. In the medium and high voltage busbar systems, the voltage drop is insignificant. The impedance of a connection is the vector sum of resistance, inductive reactance, and capacitive reactance. In a busbar system, the inductive reactance is far greater than the capacitive reactance, and hence the capacitive reactance is neglected in calculations. Sandwich bus design inherently exhibits low inductance and high capacitance and is therefore ideally suited for low voltage connections where voltage drop needs to be constrained. In a distribution network, the connected load is inductive. It operates at a lagging power factor. A distribution network will be most efficient when it operates at unity power factor. It is, therefore, the practice to have capacitor compensation to improve the network power factor. Conductor configuration. In an AC busbar system, identical conductors under different configurations can yield different resistance and inductance values. Proximity effect and flux linkage are dependent upon the conductor configuration. While transposition is carried out to ensure a balanced voltage at the receiving end of a long connection, interleaving, paired phasing and closed coupling are carried out to reduce the inductance and proximity factor. When conductors with a specific profile are held in a symmetrical configuration, they behave like a paired phased conductor arrangement, resulting in low inductance. Transposition. A phase unbalance is created by the asymmetrical disposition of conductors with respect to each other and the enclosure that is earthed. This is of concern in long low-voltage bus duct. The unbalance will be proportional to the length of the bus duct. Unbalance can be compensated by transposition. The entire route length can be divided into approximately 3 equal sections and 2 phase transpositions can be introduced. Interleaving. In this arrangement, phase conductors are split in 2 or more parallel paths and interleaved. Interleaving of the conductors not only significantly reduces the shape factor, resulting in a low resistance, consequently increasing the ampacity, but also results in low reactance. These are effective only when the flat bus bars are located close, in a parallel plane with respect to each other. Interleaving is adopted in AC low-voltage high-current open busbar connections such as arc and induction furnaces to reduce losses and voltage drop. Paired phasing. In this arrangement, the current in a conductor is split into 2 parallel paths and paired with a conductor of another phase. The current in each conductor of the pair will be equal in magnitude and opposite in direction. Conductor configuration for paired phasing. Such configurations are incorporated in non-segregated and segregated phase bus and cable bus. Conductor profiling for paired phasing. A similar effect can be achieved by profiling the conductors and configuring them as shown in Figure 5.29a and b. Such an arrangement will also bring the shape factor very close to 1, making the DC and AC ampacity equal. A significant reduction in the flux around the pair will result in lower reactance. Such configurations, incorporated in low-voltage non-segregated phase bus reduce voltage drop. Closed coupling. One method of reducing the reactance is to reduce the distance between the two conductors. This can be achieved either by placing the conductors concentrically or by bringing them closer with a high dielectric medium in between. Concentric conductors can be used for single-phase applications, while the flats interposed with insulation sheets are extensively used in sandwich busways. Induced losses. Metallic enclosure material will generate losses when enclosing conductor carrying alternating currents. The quantum becomes significant with the increase in the current rating of the conductor. The amount of heat generated will depend upon, among other factors, the type of material. The enclosure must not only be capable of dissipating the heat generated by the conductor but also the heat generated by itself. Any metallic object close to an alternating current carrying conductor will experience an induced voltage. This voltage will generate an eddy current in a closed loop, resulting in losses. These are called eddy current losses. If the metallic object also happens to be of a magnetic material, apart from eddy current losses, it will also generate hysteresis losses. These are sometimes referred to as parasitic losses. Eddy current losses. A current passing through a conductor will develop a magnetic field around it. If the amplitude of the current varies with time, the magnetic field also will vary with time. Any metallic object in the vicinity that is subjected to the varying magnetic field, cuts through the magnetic lines of force, will generate an induced voltage. This induced voltage will cause a current to flow through the metal in a closed circuit. This is called the eddy current. The direction of the induced eddy current will be such as to produce a magnetic field that will oppose the magnetic field produced by the current in the conductor. The energy loss is proportional to the square of the frequency and square of the maximum flux density. Hysteresis losses. Any magnetic material in the vicinity of alternating current will generate losses due to hysteresis. This loss is caused by the magnetization and demagnetization of the magnetic material, as current flows in the forward and reverse directions. As the magnetizing force, current, increases, the magnetic flux increases. But when the magnetizing force, current, is decreased, the magnetic flux does not decrease at the same rate, but less gradually. Therefore, when the magnetizing force reaches zero, the flux density still has a positive value. For the flux density to reach zero, the magnetizing force must be applied in a negative direction. The energy loss is proportional to the frequency and maximum flux density to the power of Steinmetz constant. Steinmetz constant varies between 1.5 to 2.5 and it is 1.6 in case of steel. The relationship between the magnetizing force H and flux density B is shown in a hysteresis loop. It is often referred to as BH loop. The locus of the tip of the loop, for various magnitudes of the magnetizing force, is called a hysteresis curve. The area of the hysteresis loop quantifies the energy required to complete a full cycle of magnetization and demagnetization. This area, therefore, represents the energy loss due to hysteresis per cycle of magnetization and demagnetization. The area of the loop is also dependent upon the flux density and varies proportionally to its maximum value with an exponent depending upon the material. Power loss and capitalization. One of the major constraints in the design of a busbar system is the maximum temperature a component can reach during normal operation. The limitation on the maximum temperature may be imposed by several factors, including but not limited to health and safety concerns, the capability of the insulation system, the capability of the conductor to retain physical properties. In a busbar systems, heat is generated by resistive losses generated in the conductor, resistive losses generated in the enclosure and support structure due to eddy currents, resistive losses generated in the enclosure due to circulating currents as in the case of continuously bonded isolated phase bus, hysteresis losses generated in steel enclosure and support structure due to the stray field. Energy for the heat generated will be fed from the system and a running cost can be assigned to it. This can be capitalized based on the expected life. Kelvin's law states that the economical cross-section of the conductor is that for which the cost of the annual joule losses is equal to the annual amortization charges for the conductor, plus other constructional elements proportional to the weight of the conductor. While it is easier to calculate the conductor losses, it is quite difficult to estimate the induced losses in the enclosure and the adjacent structure. Consequently, the losses are not capitalized for busbar systems other than that for isolated phase bus, since conductor and enclosure losses in a continuous isolated phase bus can be calculated to a fair degree of accuracy. Principle of similitude. When it is expensive to test a full-scale model to evaluate the resistance, inductance, voltage drop, and power loss, it makes sense to scale down the model. Consider two round conductors of radius A, separated by a center distance d, having a resistance R and an inductance L. If all the dimensions are halved to A by 2 and D by 2, the resistance will become 4 times R, while the inductance will remain L. The skin effect and the proximity effect will remain the same for a ratio of root of frequency by resistance. It is necessary to test the setup at 4 times the frequency. If the area is reduced by half, it is necessary to test the setup at 2 times the frequency. The resistance drop will be 4 times than at the rated current. Since the inductance remains the same, the reactance drop will be 4 times than at rated current. The resistive and inductive drops retain the same proportion. The scaling down can be generalized to any indices n. Mr. Balachandran graduated with a bachelor's degree, B.Tech, in electrical engineering from the Indian Institute of Technology, Madras, India, in 1967, and obtained a master's degree, M.E., in power engineering from the Indian Institute of Science, Bangalore, India, in 1970. He is a Fellow of the Institution of Engineers, FIE-India, Fellow of Institution of Engineering Technology and Chartered Engineer, FIET-UK, and Life Senior Member of the Institution of Electrical and Electronics Engineers, IEEE-US. He was the founder-director of Power Gear Limited and Busbar Systems, India, Limited. He has worked in manufacturing industries in India and the UK and is currently an advisor. He has engineered several busbar systems that have been manufactured and installed in various countries, including isolated phase bus for the largest hydroelectric power plant, 26 by 800 megawatts, at the Three Gorges project in China. During his professional career, he has developed and tested a range of bus products and their accessories. His area of interest also includes switchgear, instrument transformers, and power system analysis. The book, An Introduction to Busbar Systems, authored by V. Balachandran, is case-bound, hardcover, size A4, 386 pages, printed on 100 GSM glossy paper. Copies of the book can be purchased with a requisition to Bala at busbarsystems.net. Black and white version of the book is for sale in India, Afghanistan, Bangladesh, Bhutan, Nepal, Pakistan, and Sri Lanka at a cost of 4,500 Indian rupees plus freight. Color version of the book is for sale in all other countries at a cost of US $126.00 plus freight.